In this video, I'm going to explain quantum physics in a way that will turn you into a defender of it. After all, if you're watching this video, it's because you're made of stable matter. And what explains the stability of matter? Quantum mechanics itself. Even though it seems like madness that only happens in the microcosm, it's what holds everything together and ensures that matter is as we know it. Quantum theory is one of the most successful and tested in science. It's the basis for innovations we use daily, such as lasers, microchips, and in the near future, quantum computing. But the big question is, do you really understand what quantum mechanics is? Why does it seem to make no sense in our macro world? Well, I guarantee you'll leave here seeing how it makes sense. Yes. Furthermore, I'll also show you that the famous representation of the atom you know and learned in school is actually wrong. Stay until the end and I'll show you what an atom really looks like. Come with me. You know, I even like studying on paper, but that's not always the best way to study, especially when the subject is complex. Where did I read that again? Until I found the best way to study using PDF 2.0, the PDF editor with integrated artificial intelligence. But it's not just an editor. PDF AI uses GPT-5 and DeepSeek R1. To understand what I'm reading, I can talk to the PDF, translate, create mind maps. And it also has Deep Research, a tool geared towards academic research, which searches, analyzes, and connects data from different articles, facilitating the study of complex topics and helping you organize ideas based on various sources. A sensational tool. And I can even search for different keywords and find related articles. Furthermore, I can edit a passage as if it were a Word document. I can adjust images, rearrange pages, and delete or export specific sections. And best of all, with a single license, I can use PDF on all platforms: Windows, Mac, iOS, and Android, and on up to 4 devices. So, if you work on more than one device, like a computer and also on your cell phone, this is very useful. And now, during the Black Friday special offer, you can download and test PDF 2.0 for free. So, if you study, work, or simply read a lot, you need to know about PDF. The links to access it are in the description and also in the pinned comment. It's impressive how everything in science and life depends on finding the right tool to see order amidst chaos. In quantum mechanics, the Schrödinger equation is that tool. It all started at the beginning of the last century, when classical physics ran into trouble. It worked perfectly for removing cannons or calculating the trajectory of planets. But when scientists looked at small things, the calculations simply didn't add up. One of the biggest mysteries was why electrons, which are negative, don't fall into the nucleus, which is positive, as Newtonian physics predicted. That's when Max Planck, in 1900, took the first step, proposing the idea that energy is not continuous, but rather released in discrete packets, which he called quanta, the seed of everything. De Broglie showed that if these quantized orbits exist, then electrons must be waves. And this new physics, which treated energy and matter in discrete and strange ways, advanced rapidly. But one thing was missing: a unifying rule. Finally, in 1926, the Austrian physicist Erwin Schrödinger gave us the Schrödinger equation, which changed everything. Essentially, it's a wave equation, but don't worry about the mathematics, because here we'll only go over its meaning. What I want you to focus on is what we call the wave function, represented by the Greek letter psi. The wave function holds all the information we can know about a quantum system, like an electron. The movement of an electron is not described by a precise trajectory like that of a ball. It is described by the evolution of the wave function over time and space. Let's break this down further. In the classical world, waves on a lake describe something physical. They are water molecules moving. But the psi wave is not a material wave in physical space. Instead of describing where the particle is, it describes how likely it is that the particle is there. The physicist Max Born gave the key to interpreting this wave. If you take the square of the magnitude of the wave function, the result you get is not the exact location of the particle, but rather the probability density of finding that particle in a given location if we make the measurement. It's like a traffic density map. Where the map is more intense, there is a greater probability of finding the electron. But we will never know the electron's position before we look. Only after we do. That's why we say it can be everywhere, that it exists as a superposition of all possible locations with the probability of each one defined by the wave function. This seems strange, it's true, but Bohr's rule didn't aim to explain the quantum world. It only shows what we will see of it if we make the observation. We don't know what's happening to the electron until we look at it. We can see this through the double-slit experiment. Imagine you have a cannon that shoots individual electrons against a wall that has two very small slits. Behind this wall is a detector. If we were talking about good balls, we would expect to see two bands behind each slit on the detector. Something simple. Now let's shoot electrons, one at a time. The electron is a particle, so it should pass through one slit or the other. In the end, the result should be the same as with good balls, two bands. But that's not what happens. What appears on the detector is an interference pattern. Several bands, light and dark, as if the electron were behaving like a wave that passes through both slits at the same time and interferes with itself. It's as if the electron, when fired, doesn't have a defined trajectory, but rather exists as a wave function that spreads out, passes through both slits simultaneously, and only then collapses at a specific point in the detector, following the probabilities dictated by Bohr's rule that we just discussed. In other words, the experiment indicates that electrons behave like waves, but our detection indicates that they are particles. When the electron hits the detector, it is measured as a particle. Thus, we hear that when the measurement is made, the wave function collapses and becomes a localized wave, which makes it behave like a particle. The big question is that we don't know how or why this wave collapse happens. And even that has a name. It's called the measurement problem in quantum mechanics. But before I start discussing this problem, if your mind is already exploding with new information, how about you help me make even more minds explode? In a good way, of course, by liking and sharing this video. This way you show YouTube that this is quality content and that it should be shared. This contributes to the channel and also to scientific dissemination. Now, we can return to the problem. If the Schrödinger equation gives us a probability map and is highly accurate, why does this wave of probabilities instantly transform into a single real location the moment we look? Nobody knows. The evolution of the wave is never seen. But despite not knowing what is happening, there are some interpretations. One of them is the Copenhagen interpretation, proposed by Bohr and Heisenberg, which says that the collapse is a fundamental and instantaneous physical process that happens when the measurement is made and that the wave function is not real in the physical sense, but only a mathematical tool. Basically, it tells us not to try to visualize what cannot be visualized and, ultimately, to accept probability. On the other hand, we have the more intriguing interpretation, that of multiple worlds. It says that the wave function never collapses. Instead, with each quantum measurement, the universe divides into multiple realities. In one universe, the electron passed through slit A in the other. It passed through slit B in one universe. Your Schrödinger cat is alive. In another, well, it's best we don't touch on that subject. And that's why much of the scientific community adopts a more pragmatic approach. Stay quiet and calculate. That is, although we don't understand the reason for the collapse, the mathematical part of the theory works with incredible precision. So, the mystery of the wave function collapse doesn't prevent us from using the theory to build lasers, microprocessors, and even quantum computers. We simply accept the mystery and use the mathematics. This has led us to accept that we cannot know everything about the quantum world, which leads us to the uncertainty principle. Think about trying to pick up a piece of gelatin in the dark. If you try to feel where it is with your fingers, you know where it is. But the moment you touch it, the gelatin moves, that is, its speed changes and you no longer know its exact position. Physicist Werner Heisenberg formalized this idea of jelly-like particles, showing that there are pairs of fundamental properties of a quantum particle that we cannot know simultaneously, such as position and momentum. Imagine that the electron's wave function is a perfect sinusoidal wave extending throughout the universe. If the wave is perfect, we know its wavelength very precisely. By de Broglie's relation, knowing the wavelength perfectly means that the electron's momentum is perfectly known. However, this wave spreads throughout space, which means that the electron's position is completely uncertain. Now, imagine that we want to know the electron's position precisely. To squeeze the wave function and locate it at a small point, you need to sum many waves of different wavelengths, and this interference will create a more precise location. However, by using many different wavelengths, you no longer have a single value for momentum, but rather a spectrum of possible momenta. The position becomes precise, but the momentum becomes completely uncertain. We either know one or the other with precision. It's as if uncertainty is a fundamental limitation of the electron's very nature. The exact position and momentum don't exist simultaneously in the universe. Not even the universe itself knows the answer. Now, if we accept all this and know that quantum mechanics is the fundamental physics of the universe, why do these oddities only happen in the quantum world? Why can't we observe this in everyday objects as well? That's where you'll be impressed, because macro objects also propagate as waves, and we can apply de Broglie's formula to them and calculate their wavelength. Look, the electron has an incredibly small mass. When you divide the tiny Planck constant by the mass of the electron, you get a wavelength that is large enough to manifest itself. That's why it behaves like a wave and creates those interference patterns. For a tennis ball or a grain of dust, the situation changes drastically. When you take the mass of a tennis ball and put it on the bottom side of the equation, the resulting wavelength is incredibly small. In fact, the wavelength of a tennis ball moving at 10 meters per second is something on the order of 10 to the power of minus 33 meters, which is smaller than the width of a proton. Its wavelength is such an undetectable fraction of its physical size that we will never be able to observe its quantum properties. Another peculiar thing about quantum mechanics is quantum entanglement, and mystics love this. Imagine we have two entangled particles, one here on Earth and another on the other side of the galaxy. The state of one is the exact opposite of the other. If one has an up spin, the other necessarily has a down spin. Before we measure it, the Schrödinger equation tells us that both are in superposition. They can have down spin or up spin at the same time. But if you, here on Earth, measure the particle and find spin up instantly, and without any information traveling between the two, the particle on the other side of the galaxy collapses to a spin down state. At first, this seems absurd because it suggests that information would be traveling faster than light, like a spooky action. However, entanglement has been proven, and there is no violation of the theory of relativity. Although measuring the spin of one particle here on Earth allows me to know the spin of another particle on the other side of the galaxy, no information has been transmitted between the particles. They are, in fact, entangled. It's as if they decided their states before being sent away. And when I make the observation, I am collapsing their combined state. This allows us to say that the universe is not locally real. If you want to know more about this discovery, I have a video just about it right here. And as we discover new things, we need to detach ourselves from the certainties of the past. A good example of this is the most famous representation of the atom. Although simple and didactic, it's not the most accurate explanation. As we've seen here, an electron cannot have both defined momentum and position simultaneously, so it cannot have an exact circular orbit. Furthermore, it's also a probability wave, which leads us to the modern representation of atomic orbitals, a model that shows where the electron is likely to be. Unlike other physics, quantum mechanics doesn't give us clues about what's happening. We only have its impressive results that show us why matter is stable, how the sun shines, and are creating the next generation of modern technology. Quantum mechanics isn't a science that exists only on small scales. It's in everything. It is everything. Quantum physics is fundamental physics and deserves our attention with much more dedication. I hope I've changed your perspective on quantum mechanics, and if this subject has fascinated you, I'm sure you'll be even more impressed to learn how the first atom arose and what the universe was like before them. Yes, they didn't appear instantaneously in the universe. Just click here. For more of the wonders of our world revealed by me, you need to subscribe to the channel and turn on notifications. Thank you so much for your time and for following me this far. I'll see you in my next video, and bye.